Imagine we want to translate a short English sentence into French. For example, you are sad. In French, tu es triste. At first, this may look easy. We might think the model can just translate one word at a time. You becomes tu, R becomes S, and sad becomes triste. But real translation is not just word replacement. The model needs to understand the full sentence and keep track of meaning as it generates the output. Earlier encoder-decoder models tried to do this by compressing the whole input sentence into one fixed representation. That works for short examples, but as sentences get longer, that single summary becomes a bottleneck. The decoder is asked to generate each French word, while depending on one compressed memory of the entire English sentence. And that is exactly where attention comes in. Instead of relying on one fixed summary, the model can look back at the most relevant input words at the exact moment they are needed. In this video, we will build that intuition step by step. First, we will see how the encoder-decoder works. Then, why it struggles. And finally, how attention helps translation, word by word. Now let us look at the basic encoder-decoder system. Before attention is added, we will use a short sentence. You are very sad. And we want to translate it into French as tu es triste. The model does not work directly with words. First, each word is converted into a vector. So the encoder receives a sequence of vector representations. In a bidirectional recurrent network, this sequence is read in two directions. One encoder moves from left to right. It reads, you are very sad. At each step, it builds a hidden state carrying information forward. At the same time, another encoder moves from right to left. It reads sad, very, are, and you. So each word now gets two signals, one from the forward direction and one from the backward direction. These are combined to create a richer representation for each input word. After that, the decoder begins generating the translation. It produces the output one word at a time. Tu, then ezes, then trezes, then tresta. So, even in this simple example, translation happens step by step. But there is still a limitation. The decoder is still relying heavily on a compressed summary of the input sentence. For short sentences, this can work. But for longer sentences, that summary can lose important details. And when that happens, prediction quality starts to go down. So the model needs a better way to recover the right information. And that leads us to attention. Now let us fix the main limitation of the basic encoder and decoder. Instead of forcing the decoder to rely on one fixed summary of the whole sentence, we let it look back at the encoder outputs whenever it needs more information. This is the core idea behind attention. After the bidirectional encoder, each input word already has its own richer representation. So for the sentence, you are very sad, the model keeps a representation for you, for are, for very, and for sad. Now suppose the decoder is about to generate the next French word. At that moment, it has a hidden state that captures what it has generated so far and what it needs next. A small neural network then compares this decoder state with each encoder output. For each input word, the model asks, how relevant is this word right now? This produces a score for every input position. Those scores are then turned into attention weights. These weights show how much focus the decoder should place on each input word at this step. So when generating tu, the model may focus most strongly on you. When generating s, the focus may shift towards r. And when generating triste, the strongest attention may fall on sad. These attention weights are then used to build a context vector. That context vector is a weighted combination of all encoder outputs. So the model gives more importance to the words that matter most right now. This context vector is passed into the decoder to help generate the next output word. And that is why attention helps. The decoder no longer depends only on one compressed memory. It can look back and recover the right information at the right time. So in translation, attention creates a dynamic context, not a fixed one. The model still generates the sentence word by word, but now with focus. So now we can see the full picture. Machine translation is not just word replacement. The model must understand the sentence and generate the output word by word. We saw how the bidirectional encoder and decoder builds richer input representations, but also why one fixed summary becomes a bottleneck. Attention solves this by letting the decoder look back at the input and focus on what matters most right now. So instead of a fixed context, the model builds a dynamic one. And that is why attention made sequence model is much more powerful. The model still translates word by word, but now with focus. Thank you for watching the video. I'll see you in the next one.